So atomic layer deposition method. Okay, so we were discussing about different thin film deposition techniques in the last class. So now we need to discuss few more. That is atomic layer deposition is the first one in that. So surface control for epitaxial growth of a single crystal. We already said that what is epitaxial growth എന്ന് പറഞ്ഞാൽ എന്താണെന്ന് നമ്മൾ പറഞ്ഞു കഴിഞ്ഞു. ഓക്കെ, കഴിഞ്ഞ ക്ലാസ്സുകളിലായിട്ട് നമ്മൾ പറഞ്ഞിട്ടുണ്ടായിരുന്നു. സോ ഒരു സിംഗിൾ ക്രിസ്റ്റലിൽ കൺട്രോൾഡ് ആയിട്ട് ഒരു എപ്പിറ്റാക്സിൽ ഗ്രോത്ത് ചെയ്യണമെങ്കിൽ നമ്മൾ അവിടെ ഉപയോഗിക്കുന്നതാണ് അറ്റോമിക് ലെയർ ഡെപ്പോസിഷൻ. ആസ് ദ നെയിം സജസ്റ്റ് അറ്റോമിക് ആയിട്ടുള്ള ലെയേഴ്സ് 1 ആങ്സ്ട്രോം 1 നാനോമീറ്റർ തിക്നെസ് ഉള്ള അറ്റോമിക് ലെയേഴ്സ് ക്രിയേറ്റ് ചെയ്യണമെങ്കിൽ യു നീഡ് ടു go for this technique. So it is originally designed for the semiconductors, okay, and oxides and nitrates. And epitaxy എന്ന് പറഞ്ഞാൽ നമ്മൾ ഓൾറെഡി പറഞ്ഞു എന്താണ്, ഇറ്റ് ഇസ് എ സീക്വൻഷ്യൽ സാച്ചുറേറ്റഡ് സർഫസ് റിയാക്ഷൻസ് ടു ഫോം എ മോണോ ലെയർ, എ സിംഗിൾ ലെയർ ഇൻ ഈച്ച് സീക്വൻസ്. അപ്പോൾ ഓരോ സീക്വൻസിലും ഓരോ മോണോ ലെയേഴ്സ് ആയിട്ട് സിംഗിൾ ലെയർ ആയിട്ട് ഒരു സബ്സ്ട്രേറ്റിന് മുകളിൽ ഉണ്ടാവും, ഒരു ക്രിസ്റ്റൽ സബ്സ്ട്രേറ്റിന് മുകളിൽ. Okay, so which is a release or exchange of ligands for the saturation of each sequence in the name. There is a ligands in the release or exchange now. Okay, this atomic layer deposition is a sequential precursor gas pulses to deposit a film on one layer at a time. Okay, so as a first precursor we will be introducing the gas will be introducing to the precursor chamber. Okay, and we will produce a mono layer of gas on a wafer surface. Okay, then we will be introducing the second precursor gas to the chamber, so which will be reacting with the first precursor to produce a mono layer of the film on the wafer substrate. So it is fundamental mechanism. If you talked about the ALD process, it is a chemi absorption and saturation process. Sequential surface chemical reaction process are the two processes that is involved in the atomic layer deposition techniques. Here you can see the atomic layer deposition for a Al2O3 aluminum oxide deposition. Okay, so here again we will be having a aluminum CH3, so it's like a trimethyl aluminum will be having, and we will be having a methyl group, and we will have a hydroxyl from the surface adsorbed H2O will be there, and which will be combined to form a reaction. In air, H2O vapor is absorbed on the most of the surface, which is forming a hydroxyl group as you can see over here. So with this silicon, it will form a silicon or hydrogen. Here the substrate is silicon. So okay, so after placing the substrate in the reactor, trimethyl aluminum is pulsed into the reaction chamber as you can see here. Okay, and the reaction of TMA, that is trimethyl aluminum, with the OH will be happening there, and methane also making a reaction product CH4 there. Okay, CH3 which is reacting with CH4 will be producing, and the trimethyl alumina react with the adsorbed hydroxyl group producing methane as the reaction product. So there will be the reaction product once the reaction happened. Okay, so in that process, the sequential ALD process, you can see the H2O then react with the dangling methyl group on the new surface, which is forming an aluminum oxygen bridge, and the hydroxyl surface group will be waiting for the new TMA pulse. Okay, and this sort of the reaction will be there, and finally the reaction product methane will be pumped away by using the gas flow cycle, and the excess hydrogen vapors does not react with the hydroxyl surface group, which getting a perfect passivation to one atomic layer will be of aluminum oxide will be obtaining through that process. Okay, so this process and the equipments we will be using that. So we already said that a recent release of sequential precursor gas plus to deposit one layer at a time, and a first precursor gas is introduced to the process chamber and produce a mono layer of gas on the wafer surface. Okay, then a second precursor of gas is introduced into the chamber, reacting with the first precursor to produce a mono layer of film on the wafer surface. Okay, so already we said that what is chemisorption saturation process and sequential surface chemical reaction process in the previous slide. You would have understood that. Okay, so here you can see that the each process and their reaction kinetics has been mentioned there. Okay, the one advantage of this atomic layer deposition is that the stoichiometric films with large area of uniformity and 3D conformality will be obtained. A precise thickness control can be done because we are doing in a atomic level thickness, and low temperature depositions are possible. Gentle deposition process for sensitive substrates, and the main disadvantage compared to the chemical vapor deposition is that the deposition rate is comparatively very slow. Okay, and the number of different material that can be deposited is fair compared to molecular beam epitaxy. Okay, so it is molecular epitaxy comparison, it is comparatively less ആണെന്ന് പറയാം. And now there is another technique which is called again a deposition technique, which is laser ablation അല്ലെങ്കിൽ അതിനെ pulsed laser deposition എന്ന് പറയും, PLD എന്നാണെന്ന് പറയാം. അവിടെ നമ്മൾ ലേസർ ആണ് ഉപയോഗിക്കുക, ഹൈ എനർജി ലേസേഴ്സ് വിൽ ബി യൂസിങ്, വിൽ ബി എ പൾസ്ഡ് ലേസർ ആണ്, കണ്ടിന്യൂസ് അല്ല, പൾസ്ഡ് ആയിട്ടുള്ള ലേസർ ബീം ആണ് നമ്മൾ യൂസ് ചെയ്യുക. സോ വിച്ച് ഇസ് ലൈക്ക് ഗ്യാസ് ലേസർ, ARF, KRCL, KRF, XCCL ഒക്കെ പോലുള്ള എക്സൈസമർ ലേസർ ആണ് നമ്മൾ നോർമലി യൂസ് ചെയ്യുക. ആൻഡ് ഓൾസോ one can use solid state lasers ആയിട്ടുള്ള നിയോഡിയം യാഗ് ലേസേഴ്സ് യൂസ് ചെയ്യാം. It will be the wavelength of each laser has been mentioned there, you can see that. Okay, and since the excimer laser ന്റെ wavelength കുറവായതുകൊണ്ട് തന്നെ അതിൻ്റെ എനർജി എന്ന് പറയുന്നത് it will be very high ആയിരിക്കും. നിയോഡിയം യാഗിൻ്റെ കേസിൽ അതിൻ്റെ ഫ്രീക്വൻസി എന്ന് പറയുന്നത് ഡബിൾ ചെയ്തതാണ്, that is why 1064 നാനോമീറ്റർ എന്ന് പറയുന്നത്. Okay, so it will be much energy will be comparatively less, but it will be double frequency ആയിട്ടുള്ള ലെൻസ് ആയിട്ട് നമുക്ക് യൂസ് ചെയ്യാം. And in that system there will be one excimer lens will be laser will be there. So we'll be having repeating at 1 to 100 hertz per second will be repeating, and we will be having a nano laser pulse durations ആണ് നമുക്ക് ഉണ്ടാവുക സെക്കൻഡ്. ഓക്കെ, ആൻഡ് ഒപ്റ്റിക്സ് ആയിട്ട് നമ്മൾ യൂസ് ചെയ്യുക UV വിൻഡോസ്, മിറേഴ്സ്, ബ്ലീം സ്പ്ലിറ്റേഴ്സ് ഒക്കെ നമ്മൾ അതിൻ്റെ പാത്തിൽ അതിനെ പ്രോപ്പർലി കൺവേർട്ട് ചെയ്യാനൊക്കെ വേണ്ടിയിട്ട് നമ്മൾ ഉപയോഗിക്കുന്ന ഡിഫറെൻ്റ് ആയിട്ടുള്ള ഒപ്റ്റിക്കൽ ഇൻസ്ട്രുമെൻറ്റ്സ് ആണ് പിന്നീട് പറഞ്ഞിട്ടുള്ളത്. ദെൻ വിൽ ഓൾസോ ഇൻട്രൊഡ്യൂസ് ഓക്സിജൻ in order to for the reactive deposition, and target we can actually rotate, and the substrate holder and heater also will be there. Okay, so that is a basic aspect of that pulsed laser deposition. Another type of deposition we already talked about is that plating. Plating is the deposition of metal films using a chemical reaction. So here we'll do two methods. One is electroplating, another one electroless plating. So in electroplating, what we do are we'll be having a electric contacts will be required, and we'll using conductive substrates there. Okay, so we'll be getting a films of micro thick films can be obtained in this case. And electroless plating, we don't need, require any electrical contacts. We can use dielectrics and conductors as a thin films by using this method. So it is a non-vacuum system. We were talking about all the other techniques are vacuum system. Now we have a non-vacuum system which has electroplating and electroless plating is there, and the application is that it can utilize for the anti-corrosion coatings and metallization formation, and gold nickel coating for wire bonding and device interconnections. In those things, when you need a deposition, we'll do this one. And also you know that gold case gold in the case like a deposit we'll be using this as a technique. And one of the simplest technique, what is the simplest chemical synthesis method on sol gel coating എന്ന് പറയുന്നത്. There we will be using a spin coating setup, or dipping or spraying a chemical solution onto a substrate. Okay, so we will be preparing a solution, but either using a spin coating, or as I said, dip casting, or a spraying, we can actually get the thin film on a substrate. That's how sol gel coating is that. So it's a stable mixture of suspended precursor particle which is mixed in a solvent. Okay, that's we call sol gel, and the gel is hardened to form a film by drying typically in air about 100 degrees Celsius. We will heat it up after spin coating or dipping or spraying the film. Okay, and the sol gel coatings, which is a non-vacuum system. Okay, again sol gel will be having metal oxides, especially metal oxide preparation. You can use sol gel method, and the sensors, optical coating, and transparent conductors can be made of using this technique. So this is how the flow chart of sol gel preparation of a nanoparticles. Okay, so he'll be having the we'll be mixing this all together, and we'll be getting silicon oxide, and we'll get a homogeneous mixture. We'll be getting drying that, and we'll be get a gel, and that zero gel will be drying, and by applying higher 1200 degrees Celsius at 1 atmosphere pressure, we will be getting a glass of nanoparticles. So this is how we'll make silicate glasses by using sol gel methods. Okay, so that's a very simple technique. Whoever knows the chemistry part, he can do execute is in a very simple nature without having a bulk setup of vacuum system and all, not needed at all. Okay, not needed at all any vacuum system for this setup. This is a very chemistry approach where you can make the thin films on a substrate that is provided. Okay, hope you are clear with the sol gel setup. Okay, so you can see the different step in one of the method to create the silicate borosilicate glasses. This is how like we do. Okay, and now the other one, the last technique we need to talk about, that is importantly molecular beam epitaxy. Okay, as the name suggests, epitaxy, we have a continuation of a crystal structure from the substrate to the film, and the single crystalline contaminant free film will be there, and we'll have a single atomic monolayer growth we will be ensuring in this process. Okay, and of course when there is a mismatch also, when there is a crystal structure നമ്മൾ ക്രിസ്റ്റൽ സബ്സ്ട്രേറ്റിൻ്റെ മുകളിൽ നമ്മളൊരു സിംഗിൾ ലെയർ കോട്ട് ചെയ്യുമ്പം ദർ ബി പ്രോബബ്ലി എന്ത് ചെയ്യാം, എക്സാക്ട്ലി സെയിം ഡയറക്ഷൻ ആവണം, സെയിം ലാറ്റിസ് കോൺസ്റ്റന്റ് ആവണമെന്നില്ല. സോ ലാറ്റിസ് മിസ്മാച്ച് എന്ന് പറയുന്നത് ഈ ഒരു മെത്തേഡ് വഴി ചെയ്യുമ്പം ഇറ്റ് ഈസ് ലെസ് ദാൻ 1% ആണ്. ഓക്കെ, ലാറ്റിസ് മിസ്മാച്ച് എന്ന് പറഞ്ഞ് ആ രണ്ട് ക്രിസ്റ്റൽ സ്ട്രക്ചറിൻ്റെയും ലാറ്റിസ് കോൺസ്റ്റന്റ് തമ്മിലുള്ള റേഷ്യോനെ സൂചിപ്പിക്കുന്നതാണ്. Okay, so this process will do in a ultra high vacuum of 5 into 10 raised to minus 11 ടോറിനേക്കാളും ലെസ് ആയിട്ടുള്ള വാക്വത്തിലാണ് നമ്മൾ എന്ത് ചെയ്യുക, ഈ ഒരു പ്രോസസ്സ് നമ്മൾ വർക്ക് ചെയ്യുക. സോ ഇറ്റ് ഇസ് എ നോൺ എപ്പിറ്റാക്സി ഫിലിം, ഇറ്റ് ഇസ് അമോർഫസ് or polycrystalline films also you can do in this process. So this is a setup of a molecular beam epitaxy. So in this process, in order to monitor the size thickness of the film, there will be a reed means we'll talk about reed later. Okay, it is a kind of electron diffraction setup to monitor the thickness of the layer by each second. Okay, so this is the entire setup of all molecular beam epitaxy. Will be having a fluorescent screen, and we have a CAR assembly, ionization chamber. Okay, so we will be having a load lock, substrate loading and unload. What is load lock means, without breaking vacuum you can load your substrate and you can take back the substrate. Okay, without breaking the opening the chamber, without breaking the vacuum inside the chamber, one can do that. That is what load lock for substrate loading and unloading. And liquid nitrogen will be used to cool the wall because there will be a lot of heat will be producing. The substrate heating also will be managed by providing liquid nitrogen. Okay, so which also the substrate heating will be cleaning the surface too. And when you are doing the film growth at ultra high vacuum, the shutters will be controlling the flux, the in situ analysis, and the thickness monitoring by a reed to control the deposition rate also will be enhance the quality of the thin films that is you will be depositing through molecular beam epitaxy. So what is a reed? Reed is a reflection high energy electron diffraction. Okay, it is a high energy electrons which is of greater than 10 kilo electron volt, and which is passing through the material or the films that is formed over there at a small angle of incidence. We call it as grazing incidence. Small angle we call it grazing. So it is less than 3 degree angle, so that you will be getting the thickness of the proper films. So low depth penetration will be less than 100 angstrom, and lateral ordered structure and surface structure symmetry and lattice constant ഇതൊക്കെ ഐഡന്റിഫൈ ചെയ്യാൻ റീഡ് നമ്മളെ സഹായിക്കും. Okay, so read is one of the such technique, and you can see the read pattern, the specular reflection straight through beam pattern that will be obtained through read. You can see over here. From that read, one can actually say whether the layer is single or multiple, that we can actually say from this one. Okay, and in a molecular beam epitaxy, we will be getting a single crystalline substrate with a lattice matching to the film. Then only we can do that, because the lattice constant of the substrate and the material that you are going to coat should be comparable, so that the mismatching we can reduce less than 1%, so it will be effective to get a quality crystal films. Okay, then also you can heat the 500 degrees Celsius to 550 Celsius to remove the surface contamination. And also you can do layer by layer growth, which is controlled by high speed shutters and thickness monitor. And you can see that after one layer you want to close and you want to start another layer, so then you need a high speed shutters, and also the thickness of the each layer we need to monitor, and we need to ensure the film is uniform as well. Okay, here you can see a quantum dots which is grown using molecular epitaxy. Okay, when you see the size of this it will be order of less than 1 nanometer to 2 nanometer. So that is the order of a quantum dot that is on a entire area you can see here. Okay, so this is how a quantum dots that we can also prepare by a molecular epitaxy. It is a sudden closing of the high speed shutters will ensure the growth of the quantum dots. Okay, and we already have talked the nanostructural fabrication, like bottom up approach and top down approach, and we said about that there is a plenty of room at the bottom. Okay, and nanoparticle nanowire preparation we already mentioned. Okay, with that we came to end of that growth techniques of nanomaterial session. That is the session we were talking about, right? So in that section we all covered all the possible techniques, and there are other techniques like a sol gel also we just mentioned. Okay, so that's all about that part of the fourth module, growth techniques on nanomaterials. Okay, thank you for listening.